Hello.
How are you?
Good.
Is it very cold now in Baltimore?
It's a good weather for skiing. It should be on lecture. Very well, skiing.
Yeah, I remember we went together once.
Yes. Exactly after the lecture will be a lecture of Yefimov from Steklov Institute in Kansas
When? Today?
today.
Can you see the slides?
Yeah, I see. It is ready.
So, by the way, what happened to the JAMI conference? It was postponed last year.
I do not know. Maybe Jung knows, but he will not be maybe in our department next year.
Okay. So maybe next year.
Mm. It seems to me like one conference is planned by Bondo.
In Moscow?
Yeah, for this May.
For this year. So it will be online, I guess.
For foreigners, yes, but maybe for domestic people.
So shall we start now?
Yeah, I think so. Are you ready?
Yes.
Yes. So this is our second lecture by Caucher Birkar. You know this title about this Calabial Vibrations.
Okay, thank you, Slava and Ginger, for the introduction again. So this is the second lecture in the series about classification theory of algebraic varieties. Last time I just gave you a very general framework of the classification theory. I did not go into much detail, but in this lecture I will go a bit more into the mathematical details, but I will be focusing on part of this classification theory. So if you remember in the last lecture, when we run the minimal model program, in the end, we have several different kind of outcomes. And so basically, we say that everything is constructed from canonically polarized, or otherwise you will have vibrations by Calabials or Fanos. Now, I want to unify some of these things into one single structure. Let's just remind you of the setup. So we will work over the complex numbers for simplicity. AN will be the usual n-dimensional affine space. Pn is the n-dimensional projective space. We will be working with quasi-projective varieties. And as we saw in the previous lecture, algebraic geometry is mostly about classification of this kind of varieties. And then also we saw that Fano varieties and Calabial varieties, but we will also see their generalizations play a really important role in this classification theory. But I hope also to tell you that they are also important for other reasons if you don't even care about classification. Now, all these things fit into a general framework of low Calabial vibrations. I will start with examples and special cases, and later I will give you the more general definition. Now, so the good thing about this framework is that it covers a really wide range of different notions in algebraic geometry. And there are a lot of known results about these structures, and also there are a lot of open problems about this kind of structures. Okay, let's start with Fano varieties. Remember from the previous lecture that a Fano variety is a projective variety X with some kind of good allowable singularities and such that minus k is positive, or to be more precise, it is ample. So in the case of smooth Fano varieties over the complex numbers, they are just the manifolds with positive curvature. Now, let's look at some examples. The most basic example of a Fano variety is just a projective space. In a way, it has a very simple global geometry if you just focus on Pn itself. But of course, if you look at its subvarieties, then everything becomes complicated. And also, if you look at how Pn is related to itself, for example, just study maps from Pn to Pn, then again, everything becomes quite complicated. But individually, Pn itself is quite a simple kind of Fano variety. Now, inside Pn, if we look at hypersurfaces, hypersurface means a variety defined by one single irreducible polynomial. And if we take the degree of this hypersurface inside Pn to be at most n, then we automatically get a Fano variety. For example, if we work inside P2, then degree 1 and degree 2 equations will give you Fano varieties. In this case, they will be just lines and conics. And if we go to dimension 3, then degree 1, 2, and 3 give you Fano varieties. Now, if inside P3, if we take a conic, something of degree 2, and intersect it with something of degree 1, assuming that the intersection is nice, then we get, again, a Fano variety. So obviously, these are just degree 2 hypersurfaces inside P2. But I wrote it in this way so that just to emphasize, in the previous lecture, we looked at conic sections, that if you have a cone and intersect it with a plane, then you will get conic sections like circles and ellipses and so on. So this will give you Fano varieties. Now we can intersect several hypersurfaces. If the intersection is nice enough, in other words, if they give you a complete intersection, and if the sum of the degrees of these hypersurfaces is at most n, then again you get a Fano variety. So the previous example is one of these special cases, that you have degree 2, degree 1 inside P3, you get a Fano. So this will give you a lot of examples in every dimension. Now, if you know what a toric variety is, if you take a toric variety W, then minus the canonical divisor is large enough. To be precise, we say that it is big. And if we run a minimal model program on this Fano variety, not on the canonical divisor, but this time on minus k, in the end, we can produce something which is the ample model of W, in the sense that we can make minus k ample somewhere. So it may not be ample on W itself, but it can be ample on some other model, which is uniquely determined. And that X happens to be a toric Fano variety. So if you know toric geometry, then this can produce for you a lot of examples of Fano varieties. For example, if you just start with P2, you do some blowups, toric blowups, then you get this kind of W. And then if you do this construction, then it will give you Fano varieties. Another way of producing Fano varieties is by looking at weighted projective spaces. These are defined similar to usual projective spaces, except that you have weights associated to the coordinates. So it can be defined in a similar way by taking some kind of equivalence on an plus 1 minus the origin. So the equivalence will be given by these ways. You can also construct these projective spaces, weighted projective spaces, by taking some kind of quotient of Pn. So there are many different ways of defining them. So they happen to be Fano varieties. But also, if you take hypersurfaces inside the weighted projective spaces or complete intersections with appropriate conditions, especially conditions on the degrees. So the degree in this case, it will be similar to this example here, that we take complete intersection inside Pn, where the sum of the degrees should not be more than n. Here, the sum of the degrees should not be more than the sum of the AIs, together with some other geometric conditions. So again, this can give you a lot of examples of Fano varieties. Finally, if you take the Grassmannians of I-dimensional or L-dimensional linear spaces inside an n-dimensional space, this gives you a Fano variety. So for example, if you take L to be 1, then you just recover Pn. So we have a lot of examples. In dimension 2 and 3, there is a kind of detailed classification of Fano varieties, especially smooth one or something close to being smooth. Okay, now P1 is the only Fano variety of dimension 1. But in dimension 2, we have a lot more. Divisorial surfaces are Fano varieties of dimension 2. So it's just a different, another terminology for Fano varieties in dimension 2. They are called Divisorial surfaces. So for example, you can construct them using the historic procedure that I said, or you just take P2 and blow it up in several points. If you pick the points nice enough, then you get Fano varieties. So it can give you infinitely many, in fact, Fano varieties. Now, in dimension 3, Fano studied Fano varieties, and that's where the name comes from. And as I mentioned in the previous lecture, this was quite important for extending birational geometry or this classification theory to dimension 3. I also mentioned that in the 70s, Iskovsky and Menin, they developed these techniques of Fano, and other people like Noether and Segre. And in particular, they showed that threefold quartics, so these are hypersurfaces of degree 4 inside P4. They show that these are not rational. So this is just tells you that the geometry in dimension 3 and higher can be quite different from the geometry in dimension 2. So by contrast, in dimension 2, all Divisorial surfaces are automatically rational. So rational means that they are birational to P2. But Fano varieties dimension 3, they don't have to be birational to P3. And this is one of the examples. So this also set another wave of development. So there were a lot of works afterwards. A few years later, again in the 70s, Shokurov showed that if you take a Fano, smooth Fano threefold, and if you look at minus k, so minus k is linear to some other divisors in this particular case. And he showed that, in fact, you can find a divisor in the linear system of minus k. So this just means that there is a divisor linearly equivalent to minus k, such that this divisor itself is smooth. And in particular, this divisor is a K3 surface. So if you have Fanos, you can also produce Calabials. A K3 surface is a two-dimensional Calabial. But anyway, the importance of this result is that it tells you something about minus k and its linear system. Because in general, varieties can be understood by taking divisors or line bundles and their linear systems. So in many ways, you can use that to, for example, embed your variety into a specific projective space. And this result of Shokurov is also the origin of his theory of complements, which I will come back to later. I also mentioned that Mori proved harsh on conjecture that projective spaces are the only smooth projective varieties with ample tangent bundle, and this he did it by introducing the so-called bend and break technique, where he takes a curve inside his variety and then deforms that curve. Or to be more precise, he takes curves and morphism from these curves into X, into his variety, and then he deforms this morphism to produce rational curves. So this is the bend and break technique, and this led him to his theory of extremal rays and finally to Mori theory, or MMP, in high dimension. Okay, so as I mentioned, Shakurov introduced the theory of complements many years later, almost like 20 years later, after his result about minus k on threefolds. So what this is about, you take a Fano variety X, and then you study the linear system minus nk. So just by looking at minus k, you may not get much. But if you look at the multiples of minus k, then you get a much better picture. And he looked at these linear systems and he tried to find nice divisors. So you may not be always able to find a smooth divisor because X itself can have singularities. And so he said that in general, you should be able to find something nice in there with some kind of nice singularities. And he proved these things in dimension 2. And later he developed this theory in dimension 3 and hired a general theory together with Prokhorov. In particular, he conjectured that this minus nk should always have a nice divisor in it for n depending only on the dimension of x. And I proved that some years ago, almost like 20 years after Shakurov conjectured. So this is quite useful in many places. In particular, he used that again in the same year to show that the Borisov-Alexeyev-Borisov conjecture holds, which says that if you take Fano varieties of fixed dimension and of bounded singularity, so this epsilon law canonical means bounded singularity. I will define this later more precisely. So for example, if you take smooth one, but of course smooth one was already known. Anyway, if you take these Fano varieties with these bounded singularities, then they form a bounded family. So of course there will be like infinitely many of them, but they can all be parameterized by some finite dimensional union of varieties. And Shramov and Prokhorov, earlier they studied the birational automorphism groups of Fano varieties, and in general algebraic varieties, but in particular Fano varieties, or rationally connected varieties. And assuming this Borisov-Alexeyev-Borisov conjecture, they showed that these automorphism groups are Jordan for Fano varieties. I will come back to this point again later. I will explain it a bit in more detail. So this is interesting because it creates a connection between algebraic geometry, in particular this classification theory or birational geometry, with group theory. And more recently, Blanc, Lamy, and Zimmerman, they showed that these birational automorphism groups, in particular for Pn, so in a way, this may be the most basic and the most important example. They show that these birational automorphism groups are not simple as groups for n more than or equal to 3. The case n2 was already done by Cantat and Lamy some years ago. Okay, so that's a few things about Fano varieties just in their absolute form, in the sense that just looking at Fanos globally. But we also have Fano vibrations. Again, this was clear from the previous lecture that when you run a minimal model program, sometime in the end you get a Fano vibration. So let's just define this a little more precisely. A Fano vibration then is a vibration from X to Z, where X itself has some kind of good singularities, and minus K is ample relatively over Z. So globally, of course, X itself may not even be projective, but it's relatively X is projective over Z, and minus K is ample relatively over Z. Now, by vibration here, I mean basically just a morphism with connected fibers. So its fibers may be zero-dimensional, or even X to Z may be identity. So this is a bit of abuse of terminology, but I mean, there are other alternative terminologies, but they also are in some sense abused again. So understand vibration as just a morphism with connected fibers. And this condition of connected fibers is not so important because you can always take the Stein factorization and make it connected. So basically you have a morphism where minus K is ample relatively over some base. Now let's look at some examples of Fano vibrations. If we take X to be Fano, the usual global kind of Fanos, and you take Z to be a point, and this map X to Z to be the constant map to a point, then you already have a Fano vibration. So this is like a trivial example. But another example is if you take, let's say you start with Z, and then you take a Pn bundle over this Z. So for example, you can take Z, and then you take a vector bundle and the projective bundle associated to this vector bundle, then you get one of these Fano vibrations, Pn bundle. Another example, more complicated example, is that of a Mori fiber space. These are exactly the kind of vibrations, Fano vibrations, that you get after running the minimal model program. So they are Fano vibrations, but of a special kind. So here in these examples, the fibers are positive dimensional, but here in the next example, the fibers, general fibers, are actually zero dimensional. Here we have a birational morphism. So when you run the minimal model program, at some of the steps you get flips, and this happens when you have a flipping contraction. That, roughly speaking, means that you have a birational morphism where you don't contract any divisor, but you contract maybe some other curves, some other subvarieties of higher codimension. So this is birational, but this is still an example of a Fano vibration according to this example, to this definition here. Another type is the divisorial contractions. These are a bit similar to flips, except that you contract a divisor. You have a birational morphism, you contract a divisor, and here a minus K is relatively ample by definition. So you get another kind of Fano vibration, but another extreme kind of example is when X to Z is just the identity. So fibers are for just points, minus K is just trivially ample over X itself. However, what we are doing here is that we take a variety and we look at it locally near some point. So what we do here is singularity theory. So singularity theory is also naturally included in these kind of structures. Okay, so these are examples, and then generally you ask the question that if you have Fano vibrations, how the geometry of the total space X is related to the geometry of Z and to the fibers of this vibration. We try to understand that, and sometimes it's the other way around, that we know something about X and we want to understand something about Z, or about the fibers. So generally how we can relate all these things together, you can boil this down to many different kind of questions. I will be a bit more specific later. Okay, so we have Fanos, we have Fano vibrations, and then let me go to talk about, actually I want to talk about flipping contractions in particular, to go into a bit more details. Flipping contraction is a birational Fano vibration that does not contract any divisor, but it contracts some other subvarieties. So for example, in the case of trifolds, you can contract a curve, but not a surface. In dimension 2, flipping contractions just don't appear because if you contract something, it will automatically be a divisor. Now, they are important because they are needed for running the minimal model program. And I kind of mentioned also in the previous lecture that whether flips exist or not. So you have a flipping contraction, and the flip to exist will be equivalent to this algebraic statement that if you look at all the sheaves OX m times k, the m here are non-negative integers, and then push them down onto z and take their direct sum. So you'll get a graded algebra of sheaves over OZ. And if this is locally on Z is finitely generated, then this exactly means that the flip of F exists. We need this flip so that we can replace X with something else and continue the program. I also mentioned that Mori showed that flips exist in dimension 3 for some kind of singularity. Shokurov showed that they exist in dimension at most in dimension 3 and 4 with more general kind of singularities. And after work of Haken and McKinnon, then in the BCHM paper, we show that flips exist in every dimension. So I just wanted to emphasize that flips are also some kind of final vibration, although you don't have a genuine vibration, you have a birational morphism. Okay, now let's talk about Calabial varieties. Again, I will go through some examples and look at Calabial vibrations and so on. A Calabial variety is a projective variety with good singularities and k being trivial in a numerical sense, not necessarily linearly trivial, but just numerically trivial, which actually implies that some multiple of k is linearly trivial. So in some places, people put more restrictions on defining a Calabial variety. For example, they assume it is smooth and k is linearly trivial, is simply connected and so on. But we don't put that kind of restriction. So this is acquired very general kind of definition. And examples include elliptic curves in dimension 1. So these are precisely Calabials in dimension 1. Hypersurfaces in Pn of degree exactly n plus 1. If the degree is less than that, then you get a final. If the degree is precisely n plus 1, you get a Calabial. In dimension 2, there are different classes, groups of Calabial varieties. We have K3 surfaces, abelian surfaces, Enrique surfaces, Kummer surfaces, and so on. So there is a classification of Calabials in dimension 2. In higher dimension, abelian varieties will always give you Calabials. If we work inside Pn, again, complete intersections give you Calabials if you take the sum of the degrees to be precisely n plus 1. So this is similar to the final construction. And similarly, if we work in weighted projective spaces and take complete intersections with appropriate conditions, then we get again examples of Calabial varieties. Also, another way of constructing Calabials is that to take Y to be a Fano variety and then look at the anti-canonical system. And if you can find a smooth element there or an element with good singularities, then you automatically have a Calabial. I mean, Y doesn't have to be smooth. Even Y with good singularities sometimes give you this kind of Calabials. So these are examples of Calabial varieties. And Calabial varieties, of course, they are important in classification theory, as we saw in the previous lecture, but they are also important in other areas, for example, in mirror symmetry and its connection with mathematical physics, where it's expected that at least smooth Calabial varieties come in pairs, that they satisfy some kind of topological and other complicated geometric properties. And mirror symmetry is, of course, important in mathematical physics, but also in algebraic geometry, particularly in enumerative geometry, where you try to count the number of curves passing through certain points or with some kind of conditions. Now, let me give you also a conjecture about Calabial. That's easy to state. Suppose that we take X to be a smooth Calabial variety and L to be an F divisor. Now, F means some kind of positivity, which precisely means that the intersection number of this divisor with any curve inside X is non-negative. That's what F means. Or you can say that if you add any small ample divisor, this L plus any small ample divisor becomes ample. Then the conjecture says that this L is numerically equivalent to some other divisor, such that that other divisor is semi-ample. In other words, some multiple of this divisor is generated by global sections. Of course, here you have to take this. Otherwise, for example, if you take elliptic curves, you can find divisors which are numerically trivial, so they are NF by definition, but they are not torsion. No multiple is generated by global sections, so you have to take this numerical equivalence. So if L itself is not semi-ample, something close to it is semi-ample. And this is open already in dimension 3. Okay, now Calabial vibrations. And these are just vibrations. Again, vibration we understand in the same sense as before. This is just a morphism, a projective morphism with connected fibers. Then we say that this is Calabial if K of X is relatively numerically trivial over the base. So globally, again, X may not be projective, but relatively is projective, and it has this condition. So this is quite similar to Fano, where in the Fano case we had minus K ample over Z. Here K is numerically trivial over Z. And examples include Calabial varieties and taking Z to be just a point. Or if you take F to be a Calabial variety, and if you take the product with any other variety and take the projection onto that other variety. So again, you get some kind of trivial examples of Calabials. But more complicated examples are given, for instance, by elliptic surfaces or elliptic varieties in general. So in the case of surfaces, it means that you have a surface, for example, a smooth surface is it has a morphism to a curve, and almost all the fibers are elliptic curves. Some of the fibers may be singular, but almost all the other fibers are, except finitely many fibers, all the fibers are elliptic curves. These are called elliptic surfaces. So this is an example of a Calabial vibration. Or if you take Pn product with some variety Z, and then take a hypersurface of relative degree n plus 1. So on each fiber, you will get a Calabial, and then if you put all these things together into a family, then you have a relative Calabial variety. Okay, so we looked at Fano varieties, Calabials, and their vibrations. Now, in the Calabial case, I also mentioned a couple of known results and conjectures. Suppose that we have a Calabial vibration X to Z, and then consider other Calabial vibrations X prime to Z. So the Z is fixed here, but X itself, X is changing, such that X and X prime are isomorphic in codimension 1. So that means that outside some codimension 2 subvariety, this X and X prime are the same. So these are interesting because, for example, if you run minimal model program on a fixed variety, the minimal model program is not unique. It can give you different outcomes depending on which direction you go. And usually what happens is that in the end you get X and X prime, and they are isomorphic in codimension 1. So it becomes one of these settings. And then Kawamata showed that in this case, this rational map, this birational map from X to X prime is decomposed into flops. And flops are like friends of flips. They are some kind of, so in the case of flips, as I told you, that we have this birational map, and minus K is relatively ample, so you have a Fano vibration. But if you replace that minus k ample by k trivial, you get a relative Calabial in the birational setting, and that is actually a flop. So Kawamata showed that you can always decompose these maps into finitely many flops, which is quite interesting, because then you can, for example, try to relate the geometry of x and x prime or their topology by going one step by step. Just each flop and each individual flop is easier to understand than a rational map, a birational map like this. And there is a related conjecture of Morrison and Kawamata, which says that up to isomorphism, so here x to z is fixed. He said that they say up to isomorphism, there are only finitely many such x prime to z. So in other words, if you, in a way, if you ignore this x to x prime, the birational map, but just look at x prime itself as an abstract variety over z, then you will have only finitely many isomorphism classes. And this is a very hard conjecture, which is still wide open in dimension 3. And they were motivated by, I think, mirror symmetry. Okay, now let me go back to the minimal model program. This is basically what I said in the previous lecture, but it's not bad to just remind you. Suppose that we take W a smooth projective variety. Then we like to run the minimal model program, which gives us a sequence of birational transformations. In each step, we know what happens. You either have contracting devices, or otherwise you may have flips. But anyway, we hope that after finitely many steps, we get somewhere that we cannot continue anymore. And the program, what it does is that in each step, it tries to make the canonical divisor more and more positive by getting rid of the negativities. So in fact, each step of this program is a Fano vibration by our definition. The MMP is known in full generality up to dimension 3, but also many cases in higher dimension. But still, even in dimension 4, we still have a lot of unsolved problems. Now, one of the problems with this program is that we don't know whether it stops after finitely many steps or not. We know that we can run the program, but we don't know whether it terminates or not. And this is the so-called termination conjecture. This is still open in dimension 4 and higher. Another problem is that even if we know that the program stops at some point, let's say with x, then we still need to show that this x satisfies some nice properties. And this is the so-called abundance conjecture, which essentially says that the x, it either admits a Fano vibration, or it admits a Calabial vibration, or otherwise the canonical divisor on x is already more or less ample, is something close to ample. You can actually even make it ample. So basically, this is the classification scheme that I talked about in the previous lecture. Now, so I have talked about singularities quite a few times, but I didn't define for them precisely. Now I define them in a little bit more way, in a more general setting, where we define singularities not for just varieties, but also for pairs. In the next lecture, I will talk more about pairs and why they are important. But for now, let's just consider the singularity. So roughly speaking, a pair XB consists of a normal variety X and a boundary divisor B with coefficients between 0 and 1. So you have a divisor, just a linear combination of prime divisors of codimension 1 subvarieties, and the coefficients here, unlike in most other places in algebraic geometry where divisors always have integer coefficients, but here we take a rational coefficient or even real coefficients. But the rational coefficient is enough for us for now. So this is called a pair, and with some other technical conditions on it, but basically then a pair is just a variety and some divisor. Now, once you have a pair, you can define its singularities. And in our case, we define singularities by comparing it with a resolution of the singularities by using Hironaka's result from the previous lecture. So in other words, what we do, we take a so-called log resolution. This means that we take a birational map from some smooth variety W to X, where, of course, it removes all the singularities of X, but also it removes all the singularities of all the components of the divisor B, and pretty much anything new that may appear on W, you may have new divisors. They are also smooth, and the way they intersect each other is the best possible way, or in other words, a simple normal crossing. So if you have dimension, if you work in dimension 2, for example, then W becomes a smooth surface, and you get a bunch of curves on W. They are all smooth. They all intersect as nice as possible, just like this. That there is no common like tangent vector. Okay, so you take a resolution, and this we know that exists by Hironaka. Then we say that XB is epsilon low-canonical if every coefficient of BW is at most 1 minus epsilon. And BW is defined by this formula that you pull back K plus B, you write it down in a unique way as KW plus BW. So you get a new divisor on W, and by looking at the coefficients of this new divisor, you define your singularities. And the larger the coefficients are, the worse the singularities. And if they are bounded by 1 minus epsilon for some epsilon, then we say that the singularities are epsilon low-canonical. Now, there are many different types of singularities. I think I will just go through this quickly without paying too much attention. But if you don't know these things, just remember that we're using these resolutions to compare singularities on the resolution coefficients of some divisor to say something about singularities on XP. Now, if epsilon is 0, then the singularities are also called low-canonical. If epsilon is positive, they are also called KLT, and there are other type of singularities like terminal, canonical, and so on. But let's just look at some examples. If we take X to be a smooth variety, B to have simple normal crossing singularities, so you don't need to take any resolution because you have already resolved. There is no singularity basically to resolve. And in this case, we automatically have a low-canonical pair, or LC. If we take X to be a smooth surface, like P2, and B to be a nodal curve, a curve with a nodal singularity, then we have, again, a low-canonical pair. But if you take B to be a cuspidal curve, for example, a curve given by y squared minus x to the 3 inside, for example, in A2, then you get something which is not low-canonical anymore. It's not good singularity. Now, if you take a cone over an elliptic curve, then you get something which is low-canonical but not KLT. But if you take a cone over a rational curve of degree n, then you get something which is KLT. It is 2 over n low-canonical. So these are all kind of classical examples of singularity. Okay, now that we have some ideas about singularities and we have many examples of Farnells and Calabials, then I can define low Calabial vibrations in their most general form. A low Calabial vibration, we denote it by XB to Z. This consists of a low-canonical pair XB. So this is 0 low-canonical. And a vibration, as before, this is just a morphism, projective morphism with connected fibers, such that Kx plus B is numerically trivial over Z. So this is just similar to Calabial vibrations, except that we also have a boundary divisor here. So we work not only with K, but with K plus B. This makes the notion much more general than just working with Calabials. as we see in these examples. So examples of this include Calabial varieties themselves by mapping them to just a point, or Calabial vibrations as I defined before. But if we also take Fano varieties and Fano vibrations, then we can get low Calabial vibrations out of them. More specifically, if x to z is a Fano vibration, so minus k is by definition ample over z, then you can always find some b, which is not a unique choice, but you will have a lot of different choices, b numerically inside minus k. And that will give you then automatically k plus b will be numerically trivial over z, and therefore you have a low Calabial. So if you have Fano, then you can get low Calabial out of it. Another example is that if you have a toric pair, so here x itself is a toric variety, b is the sum of the invariant divisors, and if you have a toric map to another toric variety, then this is automatically a low Calabial vibration because k plus b is always trivial in a numerical sense. Another huge set of examples is that when you run the minimal model program on a low canonical pair or KLT, or even even smooth ones, W and C, where W, for example, is a smooth variety, C is a boundary divisor, then in the end, in some cases, you will get a genuine low Calabial vibration. By genuine, I mean with positive fibers. But even if you get something in the end like k plus b, may not be, I mean, it may be even close to being ample, but you still can get a map, for example, a birational map to some other variety where you contract some curves or sub-varieties, so you get a low Calabial vibration. Or you can simply take x to z to be identity if k plus b happens to be just ample. So in any case, we will get some kind of low Calabial vibration. Another set of example is given by taking a pair xb, let's say low canonical pair, and take z just to be equal to x. So x to z will be the identity. Then we have a low Calabial vibration, and we can still say something non-trivial or ask very difficult question about even the setting when x to z is just the identity map. In fact, we can ask many questions in general about low Calabial vibrations. So without being very precise, we can ask, for example, the following question. So if you consider a class of Calabial varieties, Calabial vibrations, and not, I mean, the whole set, but some subset, some class, you can ask what kind of conditions you should put on this class so that you have bounded families. For example, so that x is bounded, it moves in a bounded family, or z moves in a bounded family. So for example, one very natural way that this can happen is that z itself is fixed, for example. And then you take all the possible x over z, and then you ask, are they bounded or not, or what kind of conditions you should put so that they form a bounded family. As we saw in the previous lecture, this is important for moduli constructions, but it's also important for many other reasons, in fact. Another kind of general question you can ask is, if you look at minus nk, look at this linear system relatively over z, what kind of linear system you get? What kind of behavior they have? For example, can you find an element in this linear system with nice singularities or not? Similar to the case of global finals. Again, this leads you to really complicated and hard questions. Another kind of question you can ask, how the singularities on x and z behave, how are they related? For example, if you know something about the singularity of x, can you say something about singularities of z, about its fibers, and so on? And this is really important to understand the geometry of x, especially if you know something about z and the fibers and you want to say something about x itself, because this is a kind of inductive procedure. And you can also ask under what kind of conditions you have moduli spaces for some class of Calabial vibrations. I talked about this in the previous lecture, that if you have like polarized Calabials, because I did not give you the precise definition, but I said that we have a moduli space. But then if you consider something more general, for example, x to z is a Calabial vibration, then z is not a point. Do you have a moduli space? What kind of conditions you should put to have a moduli space, and so on. And you can also ask topological questions. Again, you have to put some restrictions first to take some subset of this whole set of Calabial vibration, not the entire set, so that you get something interesting. Then you can say how the topology behaves. For example, if you have Fano, what is the topology there? For instance, we know that Fanos are simply connected. So that's a topological statement. But if you take just the local case, when x is equal to z and you have x be a pair, the singularity case, you can ask about what kind of fundamental groups you have locally around a point on x and so on. So this can give you a lot of interesting questions. You can also ask under what kind of conditions is there a mirror symmetry? So mirror symmetry, because mostly people talk about it in the case of Calabial, the global case, but is there also a mirror symmetry in this relative case, generally for vibrations? Is there a mirror symmetry locally for singularities, and so on? So I think there is a lot to be explored there. And you can also ask arithmetic kind of, non-materiality kind of questions. If you work instead of over the complex numbers, if you work over a number field, what can you say about rational points on Calabial vibration? For example, just a Fano variety or a Calabial variety. Are they dense? How many you have? How they distribute, and so on. Of course, this is very complicated even in lower dimension. Okay, so that was the general framework of Calabial varieties, vibrations, and I gave you a lot of examples. And so by now you should see that this covers a very wide range of notions and problems and also known results. So I have like 10 minutes, or maybe, yeah, I have like 10 minutes here. Of course, there is a lot to talk about here, but obviously not enough time to say everything that I wanted to say. But in the previous lecture, I talked about boundedness and moduli. So let me go through this a bit quicker. Now, I talked about the boundedness of Fano varieties and also canonically polarized case, but if you have vibrations, like genuine vibrations, or even birational maps, for Calabial vibrations, you can still ask questions about boundedness. And one of the results is that if you fix the dimension on the type of singularities and also fix or bound degrees of devices that are involved here, then you can basically say that if the bases z move in a bounded family, then upstairs the total space is also moving in some bounded family. And this already has had many different kind of applications. Something related to this is a conjecture of McKernan and Shakura, which says that if you look at epsilon canonical rationally connected projective varieties X with fixed dimension such that minus K is nef, then they should form a bounded family where the epsilon is positive. So here I forgot to write, you need to fix the dimension. The dimension is fixed, the type of singularity is bounded. Instead of looking at Fanos, you take rationally connected. Now, this kind of varieties, in fact, it doesn't fit into this Calabial vibration structure that I defined. But the thing is that there is a more general notion, which are called generalized Calabial vibrations. Hopefully, we'll talk about this in the next lecture. And these varieties X in this conjecture, they simply fit into that more general setting. So this conjecture is still open in dimension 4 and higher. In dimension 3, I think it's maybe almost done.
Caucher, interrupt you. It was your mistake. It's my Kernel Prokhorov conjecture, not my. Yes.
Yeah, McKenna and Prokhorov, yes.
Yeah, yes, you said Shakurov.
Oh, sorry. Okay. Yeah, I didn't know that. Okay, yeah, this is McKenna and Prokhorov. Now there is another, in a little different direction, another very hard conjecture of Yao, which says that smooth, strictly Calabial varieties. By strictly Calabial, I mean they are Calabial by our definition, but also they are simply connected. K is linearly trivial. You have some vanishing on the cohomology of the structure sheaf. And you take the dimension to be more than 2 because in dimension 2 this does not hold. So from dimension 3 and so on, then the set of such Calabials should be bounded. There are also opposite conjectures which claim exactly the opposite of this thing. But there are very few results about this thing. One of the recent results about this conjecture is that this conjecture holds for elliptic Calabial varieties with a rational section. So in other words, if your Calabial variety X, it admits an elliptic vibration onto some base, and such that this vibration has a rational section, then those kind of Calabials will be bounded. And there is also a lot about moduli of different kind of Calabials or Calabial vibrations. For example, compact moduli spaces. We know that they exist for polarized abelian varieties. There is a long history about this subject. It goes back to like Satake, Mumford, Alexeyev. They have different approaches to this problem. And as I mentioned in the previous lecture, that we also know compact moduli exist for polarized local Calabial and also log-Fano pairs. And this later result, similar to the Alexeyev case, is based on the theory of moduli of stable pairs. Okay, so I'm almost to the end of my lecture. I have like 5 minutes. Let me also go through this page and then I will stop. Okay, let's say something about singularities and complements. I mentioned before that Shakurov and Prokhorov, they developed this complement theory. They looked at the linear systems minus nk relatively over some base when you have x to z, a Fano vibration, or even Calabial vibration. And an n complement over a point z is something like k plus delta, such that relatively over some neighborhood of this little z, we have this property that x delta is log-canonical and n times k plus delta is linearly trivial. So this is just saying that there exists some element delta in this linear system with some nice singularities, and that's basically what an n complement means. Now for Fano type vibrations, and complements, we know that they exist for n bounded, so depending only on the dimension. But there is another extremely hard conjecture of Shakurov, which says that for Fano type, but epsilon log-canonical vibrations, where the epsilon is fixed and positive, he said that KLT n complements exist for some n depending only on epsilon and the dimension. And this is proved in dimension 2, but is wide open even in dimension 3. And in fact, I think that this is one of the most important conjectures in algebraic geometry, but unfortunately, very people even know that it exists, which is really unfortunate. But it says something very fundamental about the nature of Fano vibrations, and it definitely deserves more investigation. Now, there is another conjecture of Shakurov, which is related to the previous one, which says that if you have a local Calabial vibration, which is of Fano type, and singularities are epsilon log-canonical, then on the base, you also you define some kind of structure on the base, and the singularities on the base should also be kind of bounded in the sense that they will be bounded, they will be delta low canonical for some positive delta depending only on epsilon and the dimension. Again, this is another very hard conjecture of Shakurov, even still open in dimension 3. But at least in the case when the divisor B, its coefficients are not too small, at least we have a general result that I proved many years ago that it said that the conjecture in that case holds in every dimension. Okay, so I will end the talk here, but I have quite a few more slides. So I will just go through the slides quickly so that people who watch the video later, they can read the slides. Okay, and there is something about group theory, about these birational automorphism groups and their Jordan properties and so on. Then there is also something about rationality of final varieties and rigidity, like birational rigidity. After that, there is some questions about arithmetic geometry related to Fanos and Calabials. And there is also something about coming from the differential geometry world about metrics and also case stability that originates in differential geometry, but nowadays is treated quite algebraically. And of course, also mirror symmetry and so on. So I will then just stop here.
Okay, so thank you, first of all, for your talk.
You're welcome.
And I have a question. So thank you for your talk, and I have a question. This is related to Calabial elliptic case of vibrations. Your result with Birkar, your result with Decebra and Swaldi. And you know, we discussed by email that if you have multi-section bounded, also bounded family. But my question is, so it's according to Yao conjecture, is it expected in this case that you always have bounded multi-section? Does it mean what you need to prove in this case when you have elliptic vibration?
If you have a bounded multi-section, yeah, I think it should be true.
Yeah, yes, but so in this situation, the Yao equation means that you have this bounded multi-section always.
Yeah, I think maybe not. I think the Yao's conjecture, I think, does not.
It's related to some restrictions. Maybe.
Yeah, I think that if we.
But if you put these restrictions,
that all possible elliptic vibrations should have bounded multi-section. I think it does not imply that.
But if we add this restriction by Yao, fundamental group is trivial and you have such vibration. Is it?
I'm not sure even if
that you have bounded multi-section or not.
I think not. I mean, I don't have examples to tell you, of course, but I think maybe it doesn't imply that you have a bounded multi-section.
So is it easy to prove or not?
I think, if I remember correctly, some time ago, I think, so I don't remember precisely. I'm not sure if it's correct or not. I think even in dimension 2, you can have a bounded family of surfaces with elliptic vibrations, but these elliptic vibrations don't have bounded degrees.
Yeah, but this is not a contradiction because in Yao conjecture, n is bigger equals than 3.
Yeah, of course. But I mean, the same thing, I guess, probably happens in higher dimension.
Okay, so maybe later we'll discuss this in more detail. Is any other questions or suggestions? Okay, so we will have the next lecture tomorrow about the generalized pairs by Birkar and Zhang. And so thank you for today, for your talk.
Thank you. Okay, see you tomorrow.
Bye.